Hello everybody and welcome back. We are looking at example 2 on page 67 of the workbook. And in this example, we're going to do our first example of calculating the matrix for a change of coordinates. Okay, if we read this example together, referring back to example 1, they'd like us to calculate the matrix that changes beta prime coordinates to beta coordinates. Okay, so let's remind ourselves of how the change of coordinate matrix was defined. That was in the kind of at the top of the page here. It looked like this. We called it Q, and we obtained it by taking the matrix of the identity transformation that takes us from beta prime coordinates to beta coordinates. Okay, so let's maybe start by reminding ourselves what those two bases, beta prime and beta, are. Okay, and I'm really just recopying these bases from example 1. So beta prime looked like the vectors 1 and negative 1, negative 1, and 1, 1. Okay, and then beta was just the standard ordered basis, 1, 0, and 0, 1. Okay, and now to calculate this matrix, we need to kind of think back to how we defined the matrix of a linear transformation. The idea was we wanted to start with this basis, beta prime, and substitute it into our transformation, which in this case is the identity transformation. Okay, so we will take the identity transformation, substitute the first beta prime vector in, do the same with the second. Okay, and our next mission is to go ahead and calculate the linear transformation, but since this is the identity transformation, we're going to get the same vector out that we plugged in. So IV of 1, negative 1 is still 1, negative 1, and IV of 1, 1 is still 1, 1. Okay, and the idea then is to write those two outputs, your combination of the second basis, beta. So we're asking, how do we write 1, negative 1 as a linear combination of 1, 0, and 0, 1? Okay, and then the same for 1, 1. Okay, but because beta is the standard ordered basis, it's not too difficult to fill in these blanks. Okay, so up above, we can see that to build the vector 1, negative 1, we need to put a 1 here and, oops, forgot my blank, and a negative 1 here. Okay, and then to build 1, 1, we need a 1 and a 1. Okay, and our matrix is just going to be obtained by taking those coefficients and making them the columns of our matrix. Okay, and so therefore, our change of coordinate matrix Q looks like 1, negative 1 in the first column. Okay, and then 1, 1 in the second column. Okay, and actually, we have completed the problem as it's asked. They just wanted us to calculate that change of coordinate matrix. I would like to make a couple of comments here, though. Okay, first of all, we could ask the question, is there a way that we could maybe shorten this process that we just went through? Okay, you might have noticed that the very first step that we wrote, here and here, that wasn't really necessary because we know what's going to happen if we take two vectors and plug them into the identity transformation. We're just going to get the same vectors back again. And so it's customary to maybe start at this step. When you're finding a change of coordinate matrix, really, all we have to do is to start with the beta prime vectors here and write those as a linear combination of the other basis. That's going to give us our matrix. Okay, and I'd like to make one more comment or ask a question here, I guess, and that is there a way that we could check this matrix and confirm that it really does what it's supposed to do? Okay, let's take a minute and just think about that. Okay, so to check this, here's what we can do. All right, so I'm going to start by just writing down the matrix that we just found. 1, negative 1, 1, 1. And remember what this matrix is supposed to do. It's supposed to take us from beta prime coordinates to beta coordinates. All right, so that means if we put a vector here and think of it as a beta prime coordinate, it should give us back a beta coordinate. Okay, so I'm going to choose the vector 1, 2. If you're wondering where that comes from, that actually happens to be one of the coordinate vectors on the table in example 1. We'll sneak a peek at that table again in just a minute. Okay, let's do the matrix multiplication, see what we get here. So if we start with the first row, okay, take the first row times 1, 2, we're going to get 1 times 1 plus 1 times 2. That's going to give us a 3 up here. Okay, and then for the second row, we get negative 1 times 1 plus 1 times 2. That's going to put a 1 down here. This is just ordinary matrix multiplication that we're doing. And that 3, 1 that comes out should be beta coordinates, if this matrix does what it's supposed to do. Okay, so remember those two vectors, 1, 2, and 3, 1, and we are going to page back to example 1 and take a peek at our table. And notice that if you look at the very first column, you see the 1, 2, and the 3, 1. 1, 2 were the beta prime coordinates of 3, 1, and 3, 1, those were the beta coordinates. And so our matrix took us from one set of coordinates to the other, just like it's supposed to. Okay, we can maybe try that experiment again, this time with the negative 1, negative 1 vector. Let's just go forward again and see what happens if we do that. Okay, so 1, negative 1, 1, 1. There's our change of coordinate matrix. If we take it times negative 1, negative 1, those are the beta prime coordinates that we just pointed to. We do our matrix multiplication again. Let's see. This time we're going to get 1 times negative 1 plus 1 times negative 1. That's negative 2. And then negative 1 times negative 1 is 1. Minus 1 gives us a 0. Okay, so this calculation is telling us that if we start with beta prime coordinates of negative 1, negative 1, the corresponding beta coordinate should be negative 2, 0. And notice, again, we can confirm that just by looking at these two entries. Okay, so you can think of this change of coordinate matrix as being kind of a gateway. Okay, it takes us from beta prime coordinates to beta coordinates. You could try that experiment with any point on the table that you wanted to.